Thermodynamics Lecture Part I will examine heat, temperature, thermal expansion, and three types of heat transfer: conduction, convection, and radiation. Make sure that you have a pencil, paper, a calculator with you, and that you prove each slide and write down what questions you have. Otherwise, you really won't learn much. Secondly, don't try to look at the entire lecture at one sitting. It's going to be very long, maybe 10 or 15 minutes. Find a natural breaking point and turn it off, and then turn it on again after you've rested or even the next day. Again, write down questions you have for me and see me in class, or email me at tdarcy17@gmail.com. Okay. A calorie is defined as the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. The kilocalorie is 1,000 calories, the heat required to raise the temperature of 1 kilogram of water 1 degree Celsius. The heat unit used in rating foods is actually a kilocalorie, although it is often referred to as a calorie. To distinguish it from the smaller calorie, or the scientific calorie, the food unit is sometimes called calorie, written with a capital C. So when you see 200 calories, so just think it's going to be 200,000 calories, or 2,000 calories will be 2 million calories. Because the scientific calorie is really the basis that we will work from. Now, looking at this particular example, you have a woman with an average diet that consumes and expends approximately 2,000 calories per day. The energy used by her body is eventually given off as heat. How many joules per second does her body give off? Well, you simply have to convert from calories to joules using 1 calorie, that's with a capital C, equals 4,186 joules. 1 scientific calorie equals 4.186 joules. We sometimes use 4.18 joules for a calorie. It depends on the particular book you're looking the values up in. So you're converting from days to seconds, and you come up with 97 watts, or 97 joules per second, or 97 watts, that's capital W, watts is joules per second. So this is the equation we're going to be using when we do calculations for Thermo Part I. Remember, the calculations for Thermo Part I will be tested for in quizzes when we do the unit of Thermo Part II. Now, the heat, Q is heat, stands for quantity. The heat gain plus heat lost equals 0, and therefore setting them equal to each other, heat gained equals the additive inverse of the heat lost. There are the different values. Q is energy, M is mass, delta change, T temperature, and C is specific heat capacity. And we will be using a variety of different values for the specific heat capacity. Those values will be fully explained on your equation sheet. So this is the genesis of the actual equation you're going to be using. Heat gained plus heat lost equals 0. M delta T C gained plus M delta T C lost equals 0. M delta T C gained equals the additive inverse, or negative M delta T C lost. So remember that negative sign on the right. Don't forget it. Otherwise, you'll wind up with a value that's incorrect. So make sure that you have that negative sign there on the right side of the equation. Let's do an example problem. Here we're going to find the specific heat capacity of a metal. I have 0.5 kilograms metal, 0.8 kilograms water, 100 degrees Celsius is the initial temperature of the water. 25 degrees Celsius is the initial temperature of the water. The final temperature of the system is 35 degrees Celsius. And I have a specific heat capacity of 1 kilocalorie per kilogram degree Celsius. Plugging in very nicely the delta T. You don't have to worry about T. It's TF minus TI. It's going to be 10 degrees, 35 minus 25, and 35 minus 100 would be negative 65. So that kind of comes out a little bit there on the right side. And make sure that you can verify this yourself. And the specific heat capacity is 0.246 kilocalories per kilogram degrees Celsius. And make sure that you can actually do this calculation, verify it, etc. Notice on the line one up from the bottom, you have the additive inverse there. So you're taking, it's going to be a positive 32.5. So positive 32.5 divided by 8 is going to be a positive 0.246 kilocalories per kilogram degrees Celsius. Next, this is actually going to be a relatively difficult problem when you're trying to find the final temperature. So plugging in, that's easy enough. Remember, it's TF minus TI. So make sure that you plug in correctly. You'll see the first line there. I'm just plugging in. And then I multiply 0.8 times 1 is 0.8, then 0.8 times TF, and then 0.8 times 30. That's how I get the left. And then 0.8 times 0.26 is 0.18, 0.1808. And then I distribute that. 0.180 times TF is 0.1808 TF minus 18.08. I have not yet distributed the negative sign in there, but make sure that you can get to that point. So you have 0.8 TF minus 24 equals the negative sign there, quantity 0.1808 TF minus 18.08, and quantity. So you're at that point now. You're at that point where you can now, the next thing you're going to be doing is you're going to be distributing that negative sign and coming up with the correct answer. So before we begin, make sure that you can get to that particular point. Now, it's going to be 0.8 TF minus 24 equals negative 0.1808 TF plus 18.08. Remember, you distributed that negative sign. And then I have, I'm going to add the TFs to both sides, then add 24 to both sides, and you get 0.9808 TF equals 42.08, and then TF is going to be 43. Make sure the answer is between the initial temperatures, otherwise it's wrong. So if your answer is between, then you've done it right, because if it's not between, then you did something wrong with that additive inverse sign. The next equation is going to be pretty simple, and that's simply going to be to try to find the TI, or the initial temperature of the water involved here. So plugging in 0.5 times the quantity 32 minus 0. Again, the water's on the left, the metal's on the right. You could put the metal on the left and the water on the right. It doesn't matter either way. And so you should see, once you're all, the physics is 0.5 quantity 32.0 minus TI quantity times 1 equals negative 0.8 quantity 32 minus 100 quantity 0.18. That's the physics. Everything else is math. So if you have a problem with the math, make sure you identify that it's not the physics but the math, and I can help you with that. Then solving through, and I'm going to add 0.5 Ti to both sides, and I'm going to subtract 9.792 to both sides, from both sides, and then I'm going to divide through by 0.5 Ti, and I get Ti equals 12.4 12.4 degrees Celsius will be the answer to that. Okay, why don't you take a break at this point? I'm actually going to stop recording. You won't really know I'm taking a break. But just make sure that you can do these particular problems. There's 3 problems here, and it's a good representation of what you will be required to do for the calculations for the next quiz, the next Do Now quiz that you take. We will determine many of our final answers in calculations using a wide variety of specific heat capacities: joules per gram degree Celsius, calories per gram degree Celsius, kilocalories per kilogram degree Celsius, kilograms per kilocalories per kilogram Kelvin, kilojoules per kilogram degree Kelvin, or just Kelvin, not degree Kelvin. So make sure that you know what values you have and what values you are calculating. For instance, if I'm going to convert from 4.18 joules per gram degree Celsius to kilocalories per kilogram degree Celsius, then I have to do a unit label conversion, as is shown here, because I want kilograms, kilocalories, and degrees Celsius. Just a note here, in terms of delta T, change in temperature, degree Celsius and Kelvin is the same. A change in temperature of 5 degrees Celsius is the same as 5 Kelvin. So that's something to be aware of when you're doing these problems. Now, this is a illustration that you'll see used and referred to many times while we do thermodynamics, and that is, if you're losing kinetic energy, you're heading towards absolute zero Kelvin. If you are gaining kinetic energy, you're heading away from 0 Kelvin. Just remember that most of the universe is actually very close to 0 Kelvin. It's about 2 Kelvin, approximately, because most of the volume of the universe is empty space, is no matter, no energy. So most of the universe is near 0 Kelvin, on average. These are 3 things that you should already know. That's just Fahrenheit on the left, Celsius, and Lord Kelvin on the right. Those are the 3 guys that the 3 temperature scales: Fahrenheit, Celsius, and Kelvin. Now, looking at a particular piece of material, that rock, that rock is at the same temperature as the top of your desk, for instance, but it's cold to touch. But the grand total of all the energies inside the substance is called internal energy. A substance does not contain heat, it has internal energy. So what's the difference between that and how it feels in terms of its temperature? At absolute zero, or 0 Kelvin, a substance has no kinetic energy to give up. 0 on the Kelvin scale, or absolute zero, corresponds to negative 273 degrees Celsius on the Celsius scale. So when we're talking about how something feels, does it feel hot or does it feel cold? Is that the temperature at which something is, or the ability to conduct heat? Is that the question? So let's look at the various quantities of material relative to heat content, or internal energy content, internal energy. For instance, I have a bucket, could be a bucket of warm water on the left and a cup of very hot water on the right, yet the bucket has more internal energy than the little cup on the right, even though the little cup is hot. But we're not talking about the per degree, per gram. We're talking about the total energy content. Let's look a little bit about what hot and cold means. Now, if I have hot, it means energy is going into your hand. If it's cold, it means it's going out of your hand. So the desk, if you put your hand on the desk, the top of your desk feels cool to touch, but then touch something metal and it feels very cold. Well, that's because the material is on top of your desk is in conducting heat out of your hand. But the metal is a good conductor, and that will conduct energy out of your hand. So we're talking about really energy conductors, something a good conductor or a bad conductor. And metal is a really good conductor, the top of your desk wood or some kind of epoxy resin, some kind of hard material. It would be a question of transfer. Let's look at frostbite. Now, some of these pictures might be graphic, so you may want to shut your eyes for some of these pictures. But frostbite is there a difference between frostbite and a burn from heat? Well, the burns are the same. It's the interface between where the transfer is taking place. If I touch something and it's cold, heat's leaving my hand. If I touch something that's hot, it's going into my hand. So you're causing trauma to the transfer location, to the interface with the environment. So that's what you're really doing. You're causing a trauma to the interface. And if that trauma is great enough, it's a burn. The burn is a burn. Burn can be due to cold or it can be due to hot. It doesn't matter. It can be going into your hand or out of your hand. It's still a burn. Now, first picture, if you look at it, and I said to you, that's a burn from putting your fingers on the stove, and that's what happens. The skin dies, etc. Well, if I told you that was from, putting your hands in a campfire, you would say, oh, all right, that's fair enough. I mean, it looks good. I mean, yeah, sure. But that's actually frostbite. So a frostbite or a burn from heat, burn from cold, same thing. Now, the next slide is a little grosser. You may want to shut your eyes for about 30 seconds. Now, let's say if I poured hot water onto your feet, and they got burned, that would be a severe burn. You would call that a 3rd-degree burn or a 4th-degree burn. And you're going to lose your toes, or lose a part of your toes, or lose the skin and it'll regenerate. It depends on the severity of it. But that's a serious burn. This happens to be as a result of cold. It's a cold burn. Here are hands, and they lost fingers. It could have been burned in a fire. Same thing. But kind of dramatic. But it's frostbite. And again, it's at the interface of the exchange of energy is what's being burned. And if it goes deep enough, you could lose tissue. You've heard of wind burn. Well, this person didn't have something protecting their face. You could do this in the summertime. If you're in the desert, you have this terrible heat burn to keep it from the sun, or it can be from a scarf in the winter. The wind's blowing and causing a burn on your face. Now, the next The next one is this person has maybe is going to lose part of their nose as a result of this burn. This is a serious, serious burn, and you can lose your nose. So it's always important to wrap up. Now, in the area there where we live in New Jersey, it's not going to be that cold, but again, what I say about my feet don't get cold because I don't live outside, I just visit there. Now, looking at this, energy flows from warm to cool only. If this is an example, an analogy, not an equation, but energy flows downhill. Not really, but just as water, it will not defy gravity. Energy will travel hot to cold or high to low concentrations. So just be clear on that. I'm making an analogy here where just like water will flow downhill, as in this particular example, we have a little reservoir up top, a little reservoir on the bottom, and the pipe it's going to flow naturally downhill. So energy will just flow as naturally from high energy to low energy. So that's actually a law of thermodynamics. We've now cracked the first law of thermodynamics, and that is that energy flows from high to low concentration. In terms of expansion, this could be the bridge in Belmar, for all you know, a drawbridge where you have these grates. You've all seen them, maybe not noticed them, but these are for expansion. What happens when a solid will absorb energy? It will expand, and these grates allow for an expansion. Otherwise, you'll get a buckling of the roadway. Solids and liquids will expand, characteristic of that particular matter, or that particular material. Water will expand a certain amount according to the coefficient of thermal expansion. All solids and liquids have characteristic expansion coefficients that can identify them as specific to that particular substance. So all substances, solid and liquid, expand in the same way. For instance, if I have brass and iron, which one's expanding less, which one is expanding more? Well, you can see the iron is expanding more, and it's wrapping the brass. So, hey, ask yourself a question. Given this drawing, what has a greater expansion coefficient, brass or iron? Now, when it's made, obviously, you're making it as for room temperature, but so which one is expanding more and which one is expanding less? The whole idea of a lid, say this is a lid on a metal lid on a jar. If I heat this jar, I'm going to expand the lid greater than the glass of the jar. Aluminum, for instance, has a much greater thermal expansion coefficient than glass does. So, as in a ring, the rim would be the ring. It's not swelling. People think it's going to swell, so the opening of the ring will get smaller. Well, it doesn't. Obviously, here it doesn't. The whole thing pulls wider. So that's a particular important example. Now let's look at the expansion and contraction of water. Why does Lake Tahoe never freeze? Now, in the left-hand column, very important, it's going to be the volume of water. And the temperature from 0 to 20 degrees. So you'll see that water has its smallest volume at 4 degrees Celsius. So if it's less than 4 degrees Celsius, it will expand. If it's greater than 4 degrees Celsius, it will expand the water. Therefore, if you have a constant mass, your temperature, your density is going to become greater as you go from 4 to 0 or greater than 4. So this is something that you should put in your notes, that you should have available to you for taking any test and quiz. This is very characteristic as to why water behaves the way it does. Now, for a body of water, let's say this large lake, for this body of water to freeze, where you're forming that ice up there, 0 degree water is less dense than 4 degree water, so it will float on top of it. So for the entire lake to freeze over the top, it has to be at 4 degrees Celsius, because if the top layer is at 5 degrees Celsius, it has to cool to 4 degrees Celsius and sink. So the entire lake has to be 4 degrees Celsius before the top layer can reduce its temperature and actually freeze. Again, a very important concept in this chapter. So you have, when you have heating, you have the volume decreases because ice crystals collapse. Volume decreases because ice crystals collapse. I'll explain that a little bit more a little bit later. And volume increases because molecules move faster. So those two things together combine to form that characteristic shape of water relative to volume compared to temperature. I'm going to take another break, and I'll come back, and we'll begin where we left off here. Okay? And goodbye. What is it about the shape of water that gives it its characteristic properties relative to expanding when it cools between 4 degrees Celsius and 0? Well, you have to look at the hydrogen bonding. The hydrogen bonding, these are physical bonds between the oxygen and the hydrogen. You're creating 4 bonds, basically tetrahedral, and they have a very similar crystal structure to diamonds. Diamonds are also tetrahedral, although the bonds that make this diamond are all covalent bonds, whereas the bonds that make the water crystal, well, 2 are covalent, the oxygen, hydrogen, and then you have 2 physical bonds. So you have 2 physical and 2 chemical, 2 covalent bonds and 2 hydrogen bonds. And when the water molecule forms this kind of tetrahedral structure, it's kind of an open structure, so that when water freezes and locks into this state, it's forming its structure around empty space. So it's not too easy to see here. This is the diamond structure, where you have the tetrahedral structure in carbon, where you have 4 covalent bonds forming this tetrahedral structure. A better example of this tetrahedral structure is with the next slide, where each vertex is going to be another atom of carbon. So this is kind of this tetrahedral shape. You can see that between the carbon atoms, you have this kind of dead space, and this dead space creates a lower density than if you're packing the atoms closely together. So you form this kind of open space. This open space creates the characteristic of water where its density decreases as it freezes. And this is a great picture that shows that construction of a less dense arrangement of the water. And that's specifically, solely, and only the reason when water freezes, it reduces its density and therefore floats on the warmer water. Okay? Heat from a flame causes atoms to free electrons in the end of the metal to move faster and jostle against the others. Those particles do the same and increases the energy of vibrating atoms along the length of the rod. So this is energy through conduction, essentially. Now, if your feet are cold and you put them on a rug, the rug side on the person's left foot is going to feel warmer than the one on the cold, even though the rug and the floor are at the same temperature. The floor is actually conducting the heat out as opposed to the rug, which is insulating. So if something is a poor conductor, it's a good insulator. Or if it's a terrible insulator, it's a good conductor. Now, in conduction, collisions between particles transfer thermal energy without any overall transfer of matter. So where you have in convection, you have this transfer. Here we have, it has to be touching for there to be a conduction. Now, we know that water is a poor conductor of heat, and air and water are poor conductors of heat. Here's an example of people walking on hot coals. Their feet are sweaty, full of water, and water is a poor conductor of heat, as is wood a poor conductor of heat. So that's what they can do. This isn't anything magical. Save your money. You could do this yourself. Do not do not try this at home. Do not try this at home. But essentially, what's happening is that, the air. How do you know air? How do you know air, water, and wood? How do you know they're poor conductors of heat? How do you know that? Before you even look at this example and I tell you, how do you know that? Well, air is a poor conductor of heat. That's the way a blanket keeps you warm at night. The blanket traps the air, and the air does not allow the fluid, the heat from passing through the air. So the air will trap the heat, and it won't flow. Now, wood's a poor conductor of heat because a wooden spoon won't get hot. A wooden match won't get hot. So that's why we know those are poor conductors of heat. And if you look at the next picture, what is it you notice here? Well, if you have snow on the roof, it means that the house is pretty well insulated, otherwise the snow would melt off the house. So it's a good way of telling whether or not the house is well insulated. If the house is well insulated, the heat isn't getting to the roof from the house to melt the ice and snow from the roof. So it's easier to know that. How do you know water is a poor conductor of heat? Well, if you've ever swam in the ocean or the lake, the deeper you swim, the colder the water is, because the top layer of water is not going to heat the bottom layer of water very easily. Here you have a conductor, the metal, copper horseshoe. Here you have warm water and cold water. The water will actually heat the copper. So this will transmit the heat from the warm water to the cold water. So that'll act as kind of a bridge between the two. Now, the styrofoam doesn't allow it to lose heat by itself. Obviously, some is lost, but styrofoam is used because it is a good insulator. Here I see that when a test tube is heated at the top, convection is prevented. In other words, the warm water is not going to rise. That's what I mean by it's prevented. Since the water is a poor conductor, the top water will boil without melting the ice. So if I heated the water at the bottom and I had the ice up top, the reason the ice is there is because it's being held down by a paperclip. Then the water would rise to the surface and melt the ice. So this is a kind of proof that the water is not a very good conductor of heat. Here I have convection. This is during the day. During the day, the land is warmer than the air, and a sea breeze results. So you get this flow where the air is rising over the land and falling over the water, and you produce this sea breeze. It's actually quite common, especially at the Jersey Shore. You get this breeze off the ocean. That's why in the summer times, often it's kind of nicer to the waves are oftentimes nicer in the evening because you get this land breeze and kind of opens up the waves a little bit. At night, the land is cooler than the water, so the air flows in the other direction. So the air is flowing from the land to the water, and it kind of makes for a kind of a nicer wave altogether. You get less like chop on the water as a result of that. Now, the next kind of this is all convection. Again, this is convection, and the next kind we're going to talk about is heating through radiation, which is, I think, a little interesting. Radio waves is a form of electromagnetic radiation. Remember, this unit is in part the transfer of energy from one place to another. Radiant energy is transmitted as electromagnetic waves. For instance, radio waves will or could heat something and then that be re-radiated as infrared waves. So radio waves are the longest wavelength, have the longest wavelength, and heat, infrared, have shorter wavelengths. Now, if you have a fireplace, the fireplace is heating through the conduction of infrared waves. So the hot fireplace is transmitting its energy through infrared waves. I can, again, transmit them through radio waves or infrared waves, such as a fireplace. Now, light waves, electromagnetic radiation, this is visible light waves, are also a form of radiant energy. So radiant energy is transmitted through light waves. So we've seen them transferred through radio waves, infrared, visible light, ultraviolet light, X-rays, and gamma rays. Now, the concept of fluorescence is in a fluorescent bulb it's a conversion. Fluorescence is a conversion from a short wave to a long wave, essentially. And fluorescent light is going to be from ultraviolet light to white light. That's fluorescent. Incandescence is going from the other direction, is going from infrared, is going from visible light to infrared light. So remember, this light is 5% effective as a light source, but 95% effective as a heat source. So if I'm going from white light or visible light to infrared, that's going to be incandescence. That's going to be incandescence. Now, here I have all three types of energy transfer. I have radiation through electromagnetic radiation. I have convection. I have where you have these convection waves, and I have conduction, where it's actually through touching. Here I have simply wavelengths. So I have, these are radio waves, and below are infrared or infrared and visible light. And when you increase when you decrease the distance between the waves, it actually has a higher energy content. So a smaller wavelength would be a higher frequency and actually have more energy. So does that rope in the bottom have more rope or less rope than the one on top? That would have more rope, actually. So Next, we see the idea of reflection. If I reflect the energy away, you see how I'm reflecting the light. Now that's reflecting visible light. Well, if it's reflecting visible light, and visible light is electromagnetic radiation, then it's reflecting all electromagnetic radiation. So I can reflect ultraviolet, I can reflect infrared, I can reflect gamma radiation, etc., from a reflective surface. So when that toaster will reflect light, shone on it because it's reflecting. You can see that person eating that muffin. Here I have 2 cups of coffee. Let's say these cups of coffee are the exact same temperature. We'll call it black coffee on the left, we'll call it white coffee on the right. Let's say they're exactly the same temperature. Which one is reflecting light and which one is absorbing light? Well, the black coffee is absorbing light and the white coffee is reflecting light. Therefore, the white coffee will cool off more slowly than the black coffee. Good absorber of energy, a good absorber, a good emitter. A poor absorber, a poor emitter. That's the rule. So the white coffee is a poor absorber and a poor emitter, so it will cool off more slowly than the black coffee. Newton's law of cooling. The rate of cooling is proportional to the change in temperature. If I have a very hot substance, if I have a hot toaster, that's going to cool off more quickly than a warm piece of bread on a cold counter. It's going to cool off more slowly because the rate at which something cools off will be proportional to the amount in which it has to cool. So the greater the difference, the greater the rate. Okay, now let's talk about the greenhouse effect before we conclude this unit. The greenhouse effect is essentially converting these short wave visible light rays to longer infrared waves. The atmosphere is transparent to the short visible rays and less transparent to the infrared waves. What exactly does that mean relative to the greenhouse effect and what we're studying? Everyone who has lived in an area where you have a hot summer has experienced the greenhouse effect relative to their car. The window will allow in the short wave visible light, but then the longer wave infrared light becomes trapped. And a car can become like an oven in just 10 minutes. It can go from 90 degrees outside to 109 degrees inside the car. So why do you think you don't leave young children and animals in the car in the summer? Because they can suffer greatly as a result of that. So the greenhouse effect is the visible light is allowed in. The glass is transparent to visible light. How do you know it's transparent to visible light? Because you can see in the car. And then the heat, the material in the car absorbs the light energy, and it's re-radiated as infrared light. So the heat builds up because the glass is not as transparent to the infrared light, the heat light. In the United States especially, we use something called the heat index. And the heat index is kind of a combination of humidity and heat, which makes things very hot. You could see the central part of the United States is very warm. In a later chapter, we'll look at the weather flow in those areas to kind of explain the layout of the map. But you can see the heat index from the humid areas will make, the heat index is really what it feels like. Here are some record highs in Africa, in Al-Azizia, Libya. It hit 130 degrees Fahrenheit. In Death Valley, the United States. Death Valley is very famous in the United States because it's very low. It's very, very, very low below sea level. So you can see even in the United States, it can get very warm. Those are record temperatures, of course. Record low temperatures you have in Antarctica, East Antarctica, the Vostok Station, the Dome A, Amundsen Scott area in the South Pole, and also Prospect Creek, Alaska. So you can see how it can get pretty cold, minus 128.6, minus 80, etc. Again, the greenhouse effect is the glass, in this case, is transparent to visible light, or the shorter wavelength, and the produced infrared longer wave is trapped because the glass is not as transparent to the longer wave infrared light. The inside of the greenhouse will then warm up. An application of the greenhouse effect that we study is the global warming. Is the global warming due to man-made or natural processes occurring on Earth, where the atmosphere is the glass and the Earth, or where the plants are and where we live, is the inside of the greenhouse? And the debate will rage on, but it's mainly a political debate. The scientists all agree that it's pretty much a man-made phenomenon. Now, the highest temperature ever recorded on Earth was 136.4 degrees Fahrenheit at Al-Azizia, Libya, on September 13, 1922. The lowest temperature ever recorded was minus 128.6 degrees Fahrenheit at Vostok, Antarctica, on July 22, 1983. Calculate both of these temperatures in degrees Celsius. There are the equations. You plug in 58 degrees Celsius in Al-Azizia and negative 87.2 in Vostok. Those are pretty warm and cold temperatures. Another temperature that will help you identify generally is 37 degrees is about 100 degrees, 38, 37, that's body temperature. 98.6 is 37 degrees Fahrenheit. So that's a way to try to remember things, in Celsius as opposed to Fahrenheit. The barium yttrium ceramic compound used to demonstrate superconductivity will work only if supercooled to a temperature of 125 Kelvin. What is the equivalent temperature? Degrees Celsius and degree Fahrenheit. There's the equation. So it'll be negative 148 degrees Celsius. You're simply subtracting 273 from it. Then you're using the given equation for degrees Fahrenheit. Make sure you look at my lecture on YouTube, which shows the derivation of temperature. And so it's going to be negative 234 degrees Fahrenheit for the next conversion. Now, hypothermia can occur if the body temperature drops below 37 degrees Celsius. Now remember, 35 degrees Celsius. Remember, 37 degrees Celsius is normal body temperature, so it doesn't take much. Although people have been known to survive much lower temperatures, on January 19, 1985, 2-year-old Michael Trode was found in snow near his home in Milwaukee with a body temperature of 16 degrees Celsius. If Michael's mass was 10 kilograms, how much heat did his body lose, assuming his normal body temperature of 37 degrees Celsius? There is the equation. There's the important information. Plug in to the equation. T sub 0 is T naught, that's initial, and you'll come up with a value of negative 729,000 joules. Notice we're using joules per kilogram degree Celsius. We could use kilojoules per kilogram degree Celsius. That would mean the answer would be negative 729 kilojoules. Notice it's negative because it's losing, the body is losing heat. It's relative to the body, so it's exothermic relative to the body. You have to understand what perspective you're solving this problem in. So relative to the child's body, it's giving off 729,000 joules, negative exothermic. It's very important to know, you could either do the negative sign in the calculation or sign it later because you know it's exothermic by reading the problem. Gwynn's bowl is filled with 0.175 kilograms of 60 degrees Celsius soup, mostly water, that she stirs with a 20 degrees Celsius silver spoon of mass 0.04 kilograms. The spoon slips out of her hand and slides into the soup. What equilibrium temperature will be reached if the spoon is allowed to remain in the soup and no heat is lost to the outside air? There's the specific heat capacity of the spoon. You see that it's 240 joules per kilogram degree Celsius. Plug in to the equation below. Remember, we are solving for temperature final. So when you're plugging in, this looks very, very scary, but if you take things very slowly and understand we're doing 240 joules per kilogram degree Celsius, so it's joules per kilogram degree Celsius, you're going to reduce that to 59.5 degrees Celsius. Make sure you can work out this equation, this problem, specifically and absolutely. Don't take anything for granted. If you can't come up with that specific answer, then let's go over this in class. So you should be able to come up with 59.5 degrees Celsius as a final equilibrium temperature for the soup and the spoon together, understanding that we're using joules per kilogram degree Celsius in the problem. So it's important to know precisely what you're using. Here we can see that we're using, again, joules per kilogram degree Celsius. You should be able to use any of those values. Peter is heating water on a stove to boil eggs for a picnic. How much heat is required to raise the temperature of his 10 kilogram vat of water from 20 to 100? Notice that it's going to be a positive value, even though I don't have a plus written there for 3.35 times 10 to the 6 joules. It is indeed going to be endothermic. Now, it's endothermic what? Relative to the water. Relative to the air, it's going to be, or the flame itself, it's going to be exo, but relative to the water, it's going to be endo. So the next problem is going to be Phoebe's insulated foam cup is filled with 0.150 kilograms of coffee, mostly water, that is too hot to drink. So she adds 0.010 kilograms of milk at 5 degrees Celsius. If the coffee has an initial temperature of 70.0 degrees Celsius and a specific heat capacity of 3,800 joules per kilogram degree Celsius, how hot is the coffee after the milk is added? Assume adiabatic system. In other words, all the energy is accounted for. There's no loss as a result of poor insulation. So you're solving for TF, which is the tough one, and it should be 66.3. Make sure that you can solve this problem correctly, okay? It's been quite a while since we have begun these problems, and make sure you get 66.3 degrees Celsius. You write down any questions you may have, and see you later.